Alright, so the first part, this is a three-part lesson in terms of this unit. The first lesson is totally review, things that you're already supposed to know from Math 1. So we're just going to go through that very quickly, show you how to get your numbers off the calculator, and then you will be ready to move into the second part, which I'd like to cover today. And then tomorrow we're going to hit a lot of vocabulary. Alright, so central tendencies. Central tendencies are the way to describe a set of data. And the idea is that mean, median, and mode are really good indicators of central tendencies, which is based on kind of what's the majority of the data doing. Where the median is actually the actual middle number, the average could be the same as the median if your data is fairly even on each side. Your mode, your number that's there the most, might be a better indication. I'll give you an example of that. When I grade a test and I have a student I put a 0 in for, and I do the average of the class is pulled down by that 0. But if I notice that more than half the class made 90s on the test, that would be a better indication of what the students did in the class as a whole, rather than that average being 70 something because the 0 pulled it down. Does that make sense? So sometimes you have to look at, are there outliers, numbers that are way too small or way too large for the majority of the data. That also affects not only the mean, but it affects the range of the values as well. Because if I said most of the students made between 70 and 100 on a test, but I have one kid who made a 40, that affects the range as well as the mean. So all of these are things that you learned how to calculate, except for outlier. Outlier is not something you calculate. You just kind of look at it and see where your data falls, and we can talk about that as well. So here in our first set of questions, we have two sets of data. To do the math with this, you have to put it in Stat Edit. So if everybody will go in Stat Edit on your calculator, press the Stat button and press Edit. If you have anything in any of the columns in here, it would be to your advantage to delete. Does anybody have stuff in their columns? If you do, what you have to do is go up to the top and hit Clear Enter, and it will clear the whole column. Alright, if you will enter the first set of data in L1 and the second set of data in L2, then we can get started with the calculating all at one time instead of having to go back and put another set in. So put them in L1 and then L2. And I'm only going to put the first one in, but I want you to put both of them in. And when you get done doing that, double check that you typed all your numbers correctly, because if you type one number wrong, the whole answer will come out wrong, because it's, unless you just lucked out and that didn't affect all the answers. But a lot of times it will affect a lot of them if you type one number wrong. Alright, has everybody got close to getting it all in? The idea here is the calculator can give you the mean, the median, and it sometimes can give you some numbers to help you to find the range. It won't give you the range. And the mode, well, sometimes you can get the mode and sometimes you can't get the mode easily from just looking at the list, so we might look at that as well. It doesn't give you the mode, but we can find it a little quicker. Alright, is everybody ready? Alright, so on your calculator, if you've forgotten, you go back to Stat Calculate. And under Stat Calculate, we're going to use number 1. Now, number one is one variable statistics, which means that you have all your values in one column. And for each of these problems, that's true. We put in two columns, but that's two different problems. So we're going to hit number one, and it asks you, where's the data? Now, if you have an 83, you have to type L1 in because you don't get this list. An 83 would make you have to press second and 1 to get the L1 to be next to whatever's written on your screen. But for us, L1's already in there because that's the standard one. So just go down and hit calculate. Now, does anybody have any trouble with getting that? You okay with it, Lucas? I know yours does it different, but it's okay, right? Right, but you got to tell it what column it's in if it's not in L1. Okay, so when we do the second one, you got to tell it L2. Okay, 83s don't allow you to, it automatically does L1 if you don't put it in anything else. All right, now let's go over again what each of these answers up here represent. X bar is mean, that's your average. This is the sum of the x's. So you know how you add them up and divide by how many numbers you've got? This is the sum that it added up. This here, the sum of x squared, is something it uses to do a calculation for these. And so it puts that down, but we don't ever use that part. The difference between these two is Sx is your standard deviation of a sample. And then this is a Greek letter in the alphabet. Kind of looks like a sideways 9. And that represents population standard deviation. There were 9 numbers. That's what N is telling us. If we go down, we see the lowest, the highest, the middle one, and the quartiles for the box and whiskers plot look. So while we're down here, let's go ahead and pick up that lowest and highest number and subtract them and put it under range. Our highest is 9.8. Our lowest is 2.1. So when we go in and calculate this, I would like to at least see what two numbers you subtracted that you could pull off your calculator. This is the lowest, this is the highest. And then do the subtraction and write down the answer. Now, what does it say the median on your calculator right now is? 3.3. Okay. Now, we'll have to go back up to the top because I didn't write down my mean. Remember, mean is X bar. It's the first one it gives you. What's that average up there at the top? 4.1. Okay, 4.1. Then we'll just say 4.1. Since all your numbers are one digit, usually you give one-digit answers for this, although that can vary some. All right, so now with the mode. Let's say you didn't know if there was a mode or not, okay? Well, one of the things you can do with your calculator, once you picked all that off, you want to do mode last, okay, because you want to get off this screen. And you go back to stat, and you tell it you want to sort it. And it doesn't matter if you sort ascending or descending. That's what the A and the D stand for. So I'm just going to do number 2. And you tell it what column it's in. So I do second 1 because I want to do L1 right now. And I'm going to hit enter. Now, it doesn't show me anything, but now if I go back to stat edit, my numbers are in order and I can look at them and see if any of them repeat. Does that make sense? So I can go down and I can look at them and I'm saying, well, you know what? I don't have any repeaters. So do I have a mode? No. So then I would say none. And outliers, unless you see a number that really looks like it shouldn't be there, you know, you might say, well, they don't look that different. But if you're not sure, there is a way to check that as well. But do you think there's one there that's an outlier? Well, the average is 4.1, and there's a lot of them that are close to that, right? And then mode didn't have one, and the median's 3.3. What number is too far away from those two thoughts? Okay, so 9.8 might be one. Notice I said might. To figure that out, you can use your calculator, It's not, it gives you the answer. You just have to turn on something and look at it and see if it shows you one, okay? So what you do is you go to Stat Plot, and we're going to turn on a plot. And well, we're just going to turn on number 1. So turn it on, and use the type that has the box with the dots next to it for the box and whiskers plot. If an outlier is there, it will show it to you. Does that make sense? Make sure you tell it what, I got to hit enter, hold on. Once you tell it enter on that, notice it got rid of the L2 now, and it doesn't say L2 now anymore, it just says L1. So when I want to go back and do this with the second question, you'll have to go back in there and tell it L1, or I can show you another little trick if you'd rather. And then we're going to quit because we've got that all set up, because that's all you got to do is make sure it's got the right column and which graph you want turned on. Now, the correct zoom to do for this is, I got to go down and find it. Hold on, I can't remember which number it is. I don't use it very often. Yes, zoom 9. So you just press 9, and it'll go to it for you. And it will, well, I must have something in Y equals, so ignore the line. So is 9.8 an outlier? Yeah. Probably. And if you're not sure, you can do the, hold on, I didn't hit the right thing. You can do the trace button. The trace button allows you to go and see what each of those numbers were, and it'll go over to that end and show you what that dot was in case there's more than one. Okay? So now we know 9.8 definitely is an outlier, and we should have known that in the first place because it was way far away from the others, right? But it could be that it would fit, and so that's a way you can check that. Now, if you got stray stuff like me, go to Y equals and clear out your Y equals. Now, let me show you another little trick. So you typed some of it in Y2, right? Let's say you want to move Y2 over to Y1 now that you've got it done, but you just didn't want to retype it all. Okay, but you'd really rather have it in Y1. You could type in a bunch of lists and move them to Y1 as you need them. To do that, you go up to the top and you hit second. Now mine's not going to do anything. Hold on, I'm going to quit and come out of that for a minute. Hold on. Let me put something in Y2. 3. Okay, I got 2 numbers in there. All right, so if I go over there to that column, if I get up there at the top of Y1 and I hit second Y2, it'll move that column over there for you. And that way you don't have to retype or change what you're doing. Does that make sense? You can type them all in and just move it over to L1 when you want it. And that only works if you're all the way at the top and you hit second 2, enter. It'll move everything in L2 over to L1. If you put in L3, you tell it L3. Whatever column you put up there on top of L1, it moves that column to L1. And why that would be important is because you've got everything right now set up to do one variable statistics on L1 and graph with L1. Second number 2. Can you see how it says L2 above that? So that allows you to move so you could actually put in the data for 5 or 6 problems all at the beginning of your worksheet, and then you can just move them as you need them to L1. Does that make sense? And that would save you the time of having to switch which column it is over on the other, because otherwise you're going to be switching column names, and you're going to have to tell the graph to graph something different. All right, why don't y'all try the second one, and we'll go over the answers in just a second. All right, so let's check your answers. X bar, or the mean, is 14.2. The median is 15.5. The mode is 19. The range is 21, and 0 is an outlier. All right, so in our next question, I have seen this kind of question tremendously given on standardized tests like ACT, SAT. It's a typical problem where you can use a little algebra to find the answer if you know the mathematics behind how to set up the problem. And you do know the mathematics because you know how to find a real average. Add them up and divide by how many there is. You scored an 83%, 74%, 95%, and 76% on your last 4 math tests. If you want to earn an 85 in the class, assuming that the only thing you were being graded on was test, That might be true in college. Some college professors don't give grades for anything but tests. Some college professors count quizzes and other assignments. So you're going to have a variety of different ways in college that they grade you. What must your score on the next math test be? So maybe you're only going to have 5 tests that semester, and you've already taken 4 of them, and you still want that 85, but you've had some scores that are a little bit below that, right? But that 95 is going to help you out, isn't it? Now, I want it to be 5 tests. So don't you add them up and divide by 5? Okay. So we'll say 83 plus 74 plus 95 plus 76. What's that 5th test going to be? X. Yeah, I don't know. Divided by 5 scores. We want it to come out with what average? 85. Now, one way, if you were on a multiple choice test, couldn't you put each one of them in there and just try until you got one to come out 85 if you wanted to? But since we don't have a multiple choice answer set to try answers, we're just going to do the math. What do we do when there's a number on bottom that we've learned about? Yeah, let's times it by 5. Let's move that 5 to the other side because that would make the math a whole lot easier if it was just an adding problem. So what's 5 times 85? 425. All right, so this has got to add up to 425. So we already know 4 of them. Can we just add them together and subtract?
Yeah.
Okay. So what will the total of my test grade so far be? Is what we need to know first. And I could have done that before I moved to 5, y'all. I just thought it was easier to move to 5 first. Everybody agree? Anybody else getting 328? Okay, 328 plus x equals 425. So now we're to the point where we can subtract to figure out, well, what do I need for that last one to make it go up to 425? A 90 what? Okay, is that possible? Yeah, it's not over 100. Is it likely on Miss Johnson's test? Well, I don't know. But at least it's possible. I've had students in the past, they would ask me to figure out what they had to make on the exam to pass my class, and I didn't tell them. Why? Because it was over 100. And I wanted them to try. So I said, you know, possibility, yes. So, you know, that was back when we didn't have state tests and they were taking my exam. Because I don't curve, right? Makes a difference. All right. How about y'all try this one? Have you wondered why they put percent signs on the scores? Because, I mean, when I have to put a grade at the top of your test, do I say it's percent? No, because more than likely this test was graded on how many correct answers there are, how many answers there were, instead of, you know, this question's worth 2 points and this one's worth 5 points and this one's worth 3 points. They were all worth the same amount, so, and they were no partial credit. It was all you got it right or you got it wrong type thing. So I'm thinking that's why they put percent signs. So if they put the percent sign, we should as well. So in this problem, if you said 99 plus 67 plus 83 plus 86 plus blank divided by 5 equals 90, what did those 4 numbers add up to? Okay, so once you added those together and you got 335 plus, this time you're going to take 2 more tests. Did you put 2 X's in? Okay, and it's going to be, well, actually it was divided by 6. I said 5. But it was divided by 6, so if you divide it by 6, then this number here changes to what? That's right, it changes to 540. And so in that case, I have just a little bit more math going on. Would you agree? So once you take that away and divide by 2, did you get 102%? So is it possible for a person to get a 90 average in this class?
No.
No. And when you do your homework tonight, I want you to make sure that you write a sentence that answers the question for each question. But for right now, we're in a little bit of a hurry, so we're not going to write too many answers like that. We might do a few as we go along, but not on this part. But the last one, you could have just said you must score a 97% on the next math test to earn an 85%. Does that make sense? So on this one, you would say it is not possible to make the average of 90% because you would have to score 102%, which is not possible unless somebody's giving extra credit, right? And you could actually add that to it unless somebody's giving extra credit. Does everybody understand these? We okay with that? All right. So these are 3 different things that we talked about in Math 1. The measure of variance is how much data is spread out. Is it really centrally located and you got a, you remember how we talked about bell-shaped curves and that sometimes they're skewed to the left or to the right? You know, the more that spreads out, the more that's going to skew your data. Outlier could really make it very skewed. Teachers used to make bell-shaped curves, and those teachers whose curved test grades would say, okay, the majority of the students are going to get a C. What grade do I want to be a C? And then they figure out who's on this end, who's on this end, for all the way up to an A, all the way down to an F. Well, it might be skewed a little bit more in some classes. For example, in an honors class, it wouldn't be the majority of the classes making C's. It might be B's. It might be skewed up some. And that might make it skew left or right, depending on what you've got. So variance is how spread out it is. Deviation is how far are you from the mean. So there's a standard amount that you can be out from the mean. You want that mean to be in the middle. But sometimes it's not. Sometimes the median is in the middle and the mean skewed off to one side, and that's what gives that left tail, right tail look. And then variance, well, when you look at the deviation, let's say the class average is 70. If somebody made a 65, you're 5 below. But if somebody makes a 75, they're 5 above. That's a difference of a positive and a negative value. Does that make sense? Variance takes out the thought about negatives and just talks about how far you are from the mean without the negative thought. Where, and I'm not just saying they just take the negative off. It's a math calculation because it's S squared. It's the standard deviation squared. And that gets rid of that negative and just focuses on, am I really a long ways away or not from the mean? Where the actual deviation, you can deviate positive or negative, but when you do the standard deviation, it puts all those deviations together. And I could have showed y'all how to calculate these, but to save a little bit of time, I thought we'd just let the calculator do it. If you take statistics, you'll learn how these formulas work, but I wanted to throw them in because I wanted you to see that they're doing the difference of x and x bar, each value. They're squaring it to get rid of the negatives because some of them would come out negative. And they're dividing by how many samples you have minus 1 because they want to kind of get it a little bit more accurate. If you divide by how many samples you've not got, you're including a value that might be the actual mean. So we're going to look at what do these mean in relation to the data as we go through and do some calculations. All right, if everybody would enter this data, now be careful, the decade numbers have nothing to do with it. The data is strikes. Hurricanes have been striking the United States for years. They started keeping up with it in 1851 till 2000. These are by decades so that they could say this is how many strikes there were each decade. So if you'll enter this data and go ahead and enter the next one also in L2 to save us a little time, I'll pause the video while you enter example 4 and 5's data in L1 and L2. All right, is everybody about ready to look at the answers? All right, so if I do stat calculate, one variable statistics, I put mine in L1, so I'm just going to go down here and click calculate. Frequency list is not something we use a lot, y'all. So it's not, if you need to use it at some point in time, that might be something you'd learn in a higher math class and not this particular one. All right, so here's what we've got. We're going to stay on this screen for just a minute because that's the screen that gives us the most information to write over here next to my Smartboard document. And I'm going to make my Smartboard document a little smaller so that I have the room to see this and it side by side. So first it asked me, what is the mean? Remember, mean means X bar. That's the notation for average. So my mean is 17.6 a decade, per decade. It's not per year, is it? It's per decade. All right. The standard deviation that they are wanting you to pick off is the S sub X. I'm pretty sure. Let me double check that. Yes, S sub X. Because is this all the hurricanes that ever happened? No. This is just a sampling, right, of what we've calculated. They haven't kept up with it since the world began, have they? So our standard deviation is, they usually use little s for that, although the calculator uses a capital one. I don't know why. So 3.6 is how much it's varying by. Your variance, or what we call S squared, what you will want to do to get S squared is to take this value, and we might want to keep a few extra digits, and square it. So I wouldn't do just 3.6 because that's not accurate enough. You might want to pick a bunch of these digits and keep them, because I don't have any way of doing that. That's why we left it up here for you to see. And you just, I would use at least 4 or 5 of them and square it, because that will give you a little bit more accuracy than just doing 3.6. And that will be our variance. Yeah, we'll round to a tenth. That'll be fine. 13 point. Is everybody getting 13.3? All right. So, and that'll vary a little bit depending on how many decimal places you keep. The more decimal places you keep, the more accurate it is. Because my paper says a little bit different answer, but then they didn't keep but 641, and then they squared that with 3 decimal places and got 13.06 because they kept 2 on that one. There was no rhyme or reason on what this is doing, because every time you look at it, you can do a different amount. So I'm saying let's kind of keep it to doing something similar. But just make sure when you're doing that square, you keep more digits to square, because it will make a difference in your answer. All right, so now what does this mean? Well, it means that on the average, there's 17.6 hurricane strikes per decade, and that it varies by 3.6 strikes. Now, we could even actually round these to whole numbers, and it might even make more sense, right? Because can you have part of a strike? Not really. But then again, the United States says there's 1.7 children in every household in the United States on the average. I haven't seen a 0.7 child yet, but that's what they say the statistic is. So sometimes you give one decimal place just to kind of know what's that next one going to round to, you know. And obviously, this is close to being 4. It's varying by 4 in standard deviation. All right. And the variance looks like it's varying, that square number. You can't quite explain sometimes what that variance number, how big that number is, until you look at a lot of other data. And we may look at that on one of our other problems. How about you go ahead and calculate up these 3 values for the next question and put it under part A, since you already have that, put those datas in your calculator. Go ahead and calculate that up. Now, I got to figure out what I'm doing here. Oh. Can't reach the board good enough. There we go. So this one is about hurricanes in the Atlantic Ocean, and they only are using the data from 92 to 2006. So you're finding the mean, the standard deviation, and variance for that. And I'll talk about helping you with part B here as soon as you get those values. All right, so what did your X bar come up to be for part A? 7.3, everybody agree? That's X bar for part A. What is the standard deviation for this problem? All right, 3.3. This is what I want you to do. This is a bell-shaped curve. This is what we call a normal distribution, okay? To figure out the answer to part B, we need to put some numbers under these dotted lines. Each dotted line varies by the amount of the standard deviation. So, for example, you said it was 3 point what? All right, 3.3. So if I'm already on 7.3 and I go up to the right one line, it has to go up by 3.3. So that means I'm going to add 3.3 to it and get 10.6 as that line. Does that make sense? And I'll keep doing that to get the 3 lines on this side done. I'll keep adding 3.3. So then when I add 3.3 again, this line is going to be 13.9. Does that make sense? And then if I add 3.3 again, then I'm going to have 17 points. Check me on that one. 17.2, am I right? Okay. So to find the 3 on the other side, you do the opposite. You subtract. So we'll take 3.3 off of 7.3 and get 4. Take 3.3 off of 4 and get 0.7. And then I don't think I need to calculate the other one, but I will. What's that going to be? Negative what? 2.6. All right. So this is one standard deviation out if you're in the 2 in the middle. If you have gone out 2 on each side, you have done 2 standard deviations. And if you go out to the 3rd line on each side, you've done 3 standard deviations. So let's see what the answer to this question is going to be by figuring out where my data falls. Now, I need to know what the lowest and highest number on the list is. I can either go back to my calculator and look at those one variable statistics and find the min and the max, or I can just look at the data. Either way, I just need to know what the lowest value on the data is and what the highest value on the data is so I can compare it to this chart. 3. Okay, 3 falls in right here, and 11 falls in between these two. Is 14? Okay, we'll move over past this line then. See, that's why, you know, it'd be good to make sure you got the highest and the lowest because it could make a difference. Before I changed where my line was, I was right here, and that would be in between 2 standard deviations. But when I had to go past 13.9, that put me in the 3 standard deviation range, didn't it? So my data is varying by 3 standard deviations, meaning that almost 95% of my data, well, actually more than that probably more than 98% of my data fell within 3 standard deviations. And you want most of your data to be in this hump. You don't want most of your data to be out here, right? Those are kind of getting too close to the edges and outliers and not making sense, like negative numbers. Don't make sense in this question, does it? So this is within 3 standard deviations because this is within 2 over to this side, but this side went over to 3. And because I had to go over 3 on one side, it's within 3 standard deviations totally. That's the answer to the question. How many deviations? 3 standard deviations. All right, so can you do something similar with the you try problem at the bottom? And we'll come back after you've tried that and check your answer. Turn the video back on. So when you look at your X bar being 13 and your standard deviation deviating by 2.9, if you put 13 in the middle, to get down to that 9, you would have to at least go down 2 standard deviations, right? And to get to the 17, wouldn't you have to go up at least 2 standard deviations? So since they're both the same, I deviated by 2 standard deviations to get all the data to fit. That's good. because that means that you've got the majority of your data within your standard deviation, because it gets much, much smaller once it gets past this line right here. A lot less data can be in here. The majority of your data is in here. And if you remember back in Math 1, maybe, y'all might have talked about how that this area right here is like 68% of the data. And if you go out to this line, it's 95%, I think, if I remember correctly. So that's pretty good if you can get that much of your data to fall in there and have very little out in that last section. All right. Now, let's go on to the next page, which is going to be the new part of our lesson today. That was all kind of review. But we needed to know how to do those calculations on the calculator, because we're going to have to get some numbers like those and use them to calculate our next information. So now we're going to talk about margin of error. And I know it seems rather odd that I skipped to lesson 8.5, but there were some lessons in between here on normal curves and z-values, and I didn't find that in the curriculum anymore. So I just left those out, but I didn't renumber it because I thought, well, what if I need to go back later and find it really was in there? I could come back and teach it. So I just left it and left these numbered the way they were. All right, so margin of error is the interval for which the mean population is likely to be. We just did sample population means. Sample means that you have a small group and you don't have all the data, but you found an average for that small group and you hope your population's average would be the same. Well, there's an interval that the error has to be within from the means. So, like, for example, let's say that I say the average score in this class is 70, and I'm going to allow only there to be 5% error. Then I expect your grades to be between 65 and 75. 5 either way. Does that make sense? Okay, so we got to calculate that margin of error. How much error am I going to allow in my grading process? Now, I don't want there to be 5 points. I wouldn't want there to be any areas, right? You want your score right. But that's what it could be. So here is a formula that helps you to calculate error in this type of problem. There's a z sub c, and that is a value you have to pick off of a table. And that value off of the table represents what we call a confidence interval. And a confidence interval is how confident am I in your statistics. Okay, and we'll come back and talk about that in a second. S is your standard deviation, and the square root of n is the square root of how many numbers were in your list. Okay? It's a real simple calculation, and it gives you how much your data is going to be off so that you can get an interval. Then what you do with that, to get that actual confidence interval, you write it as a between. You take the x bar and subtract your error to get the lowest value, and you take your x bar and you add it to get your highest value of what could my range be if this is my error in relation to x bar. And we say that x bar is the average. So this is like how much can my average be off on the high end, how much can my average be off on the low end, so that it would represent what's mu, and mu is your whole population. So if my data was about wolves, and I had an average for wolves, and I did this mean, this mean minus and add the error, then I could tell that based on my samples average, this is what I think my data for the real population mean would be. Because I can't go out there and count every wolf in the woods, right? Am I going to capture every wolf ever on the earth? No. I can't do that. I can't capture them all at one time and get them all counted up, because I'm going to miss some of them. Even if I tag them, I'm still going to miss some. So you estimate with error, marginal error, what your actual average for the whole population is based on what this small sample is. Now, the size of your sample can play a part in that, and we can talk about that. So that's calculation. Now, on the next page, it's probably not on the next page, probably on the same page. But on the next page, at the top of your paper, is a little box. So if you'll turn over on the back there for just a minute, you see the little box up in the top right corner? Okay, that is the numbers for the percentages of confidence error. So let's think about this. If I have success rates in doctors doing surgery, and I'm trying to figure out on the average how many, do a good job or something, when I want my confidence intervals to be down here, I sure wouldn't want a doctor that's only got a 75% confidence interval. He might not be doing too good a job because his data might be varying a little too much. So think about that, because that's kind of what these numbers mean. These are the values for Z that you plug in that formula, and I couldn't get that subscript to stay down, that Z sub C. It just went back up when I put it in the table. But these are the values you plug in for that Z that represent the number that you're going to use in your calculation. So you may have to flip back and forth as we are looking at the ones on the previous page if we need more than one value. All right, so it says, what's the mean and standard deviation of the sample? Round to the nearest tenth of a minute, because we're going to the grocery store and we want to determine the wait time customers have in the express line. He's time customers, and here are our times. So you need to put all of this data in the calculator, and then we're going to find the mean and the standard deviation of that so that we can find what the other parts of this question are. We need those two values. So I'm going to give you a few minutes to put it in the calculator and do that. All right, so we have put all of this wait time in it. Yes. We have put all this wait time in minutes in our calculator. We have done the standard deviation and the mean by doing one variable statistics, and we've rounded it off to the nearest tenth. What did you get? 5.4 and what? 1.8. Okay, so the average amount of wait time was 5.4 minutes. That's quite a bit of wait time in an express line, isn't it? Wow, somebody needs to speed it up. But it's not varying by very much. It's only varying by about a couple of minutes. But then that would mean somebody's waiting at least 7 and more, right? If you added that to it. So that's a lot. All right. So now let's look at 95% confidence interval. What's the approximate margin of error? Well, first of all, we take that standard deviation and we put that on top. Let me make a little bit more room in front there. How many numbers were in this list again? 30. And if you didn't know that, you could go look at your list and sit on the last number and it would say L30 equals that number. And that could tell you. So we're going to take that and put it inside of a square root. The last thing we're going to do is we're going to look up the confidence interval number for 95% on the page on the back. 95% has a decimal that represents Z. What does it say for the Z on the back of that paper? Does everybody agree? 1.96? I would suggest you memorize that number because that one's used more than any other number. And I would think the state would probably want to choose one of the higher ones. But I don't know if they're going to give you a little table of these values to choose from or if they're going to have that value already filled in. Or I don't really know enough about it quite yet in terms of how the state deals with that. So we're going to say 1.96 times 1.8 divided by the square root of 30. And you can do that, by the way, all at one time because your calculator is smart enough to times it and divide and do it all right because it's going to do the order of operations correctly.
If we get a decimal that whole time correct, or do you want to enter a fraction?
Oh, no, this is a decimal. This is a decimal. So what are we getting? Is it rounding to 0.6? Okay. All right, so we got our 0.6. Now, let's talk about what the next question is asking us to do because we got to take that and the question before this and find what is the actual confidence interval. So now we know the confidence interval is off by 0.6. Okay, but what does that actual interval do? Well, first of all, you take x bar and you subtract that error. So I take my x bar, which you just said was 5.4, and I subtract 0.6 from it, and that'll be the lowest value that we think the population mean could be, which is 4.8. Is less than or equal to mu is less than or equal to. This is always written as a between, and they always use the Greek letter mu because that is the correct letter for average of a whole population, where x bar is just a sample. Then take x bar plus ME, margin of error, to figure out what's the highest value on this kind of confidence interval could my average be of the whole population. 6. Okay. So now that's telling me that with this small sample, if I want it to be a 95% confidence interval, that 95% of my data will fall, the average would fall in between 4.8 and 6. That's where my average of the whole population would fall. I have a 95% confidence interval saying that my average of the whole population will fall between 4.8 and 6, where my average right now is 5.4. Now, what is the meaning of the interval in terms of the wait times? So, the average wait time at the grocery store is between 4.8 and 6. Does that make sense? You go back to the word problem, pull a few extra words, and make a sentence out of that. So how about writing one sentence down today? This would be a good one to write. That the average of wait time at the grocery store is between 4.8 and 6 minutes. Now, as soon as you finish writing your sentence, I want you to go back and redo this calculation for a 90% confidence interval and see how does that change the between statement that we just wrote and the margin of error, how much it's going to be off. Does lowering the confidence interval, how does it change it? Does it make it more error, less error? How does it widen my range or shorten my range because I changed the confidence interval to less confident number? And I'm going to pause the video while you do that. So what did you get for the margin of error in Part D? 0.5. Okay, so that means I only can be off by 0.5 of a half a minute. Okay, so that means that as your confidence interval gets smaller percentages, the error gets smaller because you're multiplying by a smaller z-value, right? Which means you can't be off as much. Okay. So then when I take my x bar, 5.4, and I take away a half, that's 4.9. And when I take 5.4 and I add the half, that's 5.9. So it came in a little bit. Does that make sense? It's not quite as wide. Now my average of the whole population time, my wait times now are telling me that I have to be between 4.9 and 5.9, which means basically about 5 to 6 minutes, right? Because there's only a minute's difference in those two. So it got a little bit shorter interval because I used a number to calculate the error that was less confident. Your interval gets shorter every time. All right, let's keep going because I think we can finish this pretty quickly here. The next questions don't take as long to calculate. So the next questions are going to be based on proportions. Proportions are called p-hat. Don't ask me why they call it a hat, but they think this symbol looks like you're wearing a hat. But it's the caret key off the calculator, right? But what they're saying is that if you put a caret key over p, it's called p-hat. It's the desired number you want over the total number. all it is just a fractional what you would say the proportion is. Like, if you have 3 bread balls out of 5 balls, then you have 3 out of 5. Does that make sense? That's all they're talking about here. Okay. So in question number 2, it says, what is the sample proportion for each situation? Write the ratios as percents rounded to the nearest tenth. And it gives me some values here. All right. So first of all, we have to read the scenario and figure out what p hat is first as a fraction. So p hat is equal to a poll of 1,800, I'll get it right in a minute, 1,085 voters selected at random, 564 favor candidate A. So obviously the lower number needs to go on top, right? Because you can't have more than 100%. So 564 over 1085 is my fraction. So we'll divide that off and get a, let's say, 3 decimal place answer if it has that many. You always want your percent problem to have at least 1 decimal place, so it takes 3 decimal places to get a percent with 1. So does it have 3 decimal places, or is it shorter than that? It has it? So point what? 519? Everybody agree? So the reason you want 3 is because then you're going to move the decimal over twice and put the percent sign on it, and that way it'll have your tenths that it's talking about here. Does that make sense? It says write it a ratio, so I did, that's a ratio. It says percentage rounded to the tenths, so I had to have 3 decimal places so that this answer came out with only tenths. Alright, so in the next one we're flipping a coin. We've tossed it 40 times, it's come up heads 25. I think if I tossed it 40 times, I would have thought heads would have been 20. I got more heads than a half, right? Well, sometimes that happens when you're doing these problems. In the real world, when you experiment, things don't always come out to be what the theoretical probability is, which you studied last year. So 25 out of 40 is what decimal? And then that makes it 62.5% if I move the decimal over, correct? All right. Any question about how to find p hat? Is that pretty easy? I think that's pretty easy. Now, when you're using it in calculations, you want it before it's turned to a percent, or you'll want to use the fractions one. You have choices. I think that most students find that it really doesn't matter whether you use fractions or decimals, but you can't use the percent when you're doing the margin of error calculations. So I just usually use the fractions because they're the most accurate. So in the next question set, we're going to calculate this. This is a different formula from the previous one. It says p hat times 1 minus p hat. And what that means is, what's the probability I can get it? What's the probability I can't get it? Think about it. If it's 3 out of 5 I get a red one, then it's 2 out of 5 I didn't get one, right? So you would multiply those together. You would divide it by how many n is, which would be the total, whatever number's on the bottom. Square root that and put z, whatever confidence interval you want, in front, and that gives you your margin of error. Then your confidence interval, the way you write it is you take the p hat minus that error, or the p hat plus that error, and p in the middle is the probability of the whole entire population, where if it has a hat on it, it's a sample population. So that's just notation. So now, it says find the sample proportion, margin of error, and a 95% confidence interval for the problems that here, and we have 2, so I'll do one, let you do one. Alright, so for p hat, I have surveyed 530 people, so that's the bottom number because that's the total sample. Selected around the high school students. 280 preferred watching football to watching basketball, so I put 280 on top. Then, if this is a decent decimal, I turn it to a decent decimal, but probably it's not. So I'm just going to drop the zeros and say 28 over 53 because it's probably not a decent decimal. Now, to do your margin of error, and again, if you want to divide that out and get a decimal, you could store it in a letter. And if you want to do that, you could. I'm not going to do that, but that's another way of doing it. I want my margin of error to have a confidence interval for Z that is 95. So that's the number that I've asked you to memorize, which is 1.96. Then we're going to take the square root. Now, what's the bottom number for N? How many people did I talk to? 530. It's always whatever the bottom number on your original problem was. Then I'm going to take this fraction, 28 over 53, and I'm going to multiply it times whatever 53 minus 28 is, because I want to figure out how many people didn't say that. So what's 53 minus 28? How much? 25. So that's the probability they didn't watch football instead of basketball. So you've got to have a fraction for the p-hat, and you got to have a fraction for what's the difference of it and 1. So it's just easy to subtract the bottom and the top, put it back on top. Now, you've got to multiply these two together, divide it by this, square root it, and then times this. I wouldn't try to do all that at one time. It's a little difficult. So let's first put in fraction 28 53rds times 25 53rds and hit enter. All right, has everybody got that? Divided by 530, hit enter. Now hit square root and go up there and hit second negative key and get the word answer. And hit enter. And then take that times 1.96 and hit enter. All right, what are we getting for our margin of error? And I think we should probably write at least 2 decimal places, probably. At least. Maybe 3. Let me see. 0.0425. Well, we could write that many. Did anybody else get that? Might want to round that off a little bit more than that, because our confidence interval only has 2. Maybe let's round it to 3, because Z only has 2 on it. So that would make that a 3, and 2 would make it go up to 3 because it was 5. Since this is the only decimal in the whole problem, you probably want to make your answer match what Z was. So now, let's see if we can write our confidence interval for this using that error. So we're going to say 28 over 53 minus that decimal. And I'm running out of room here, so I'm just going to write down here, but I hope you have room. What does that come out to be? 0.485 is less than or equal to P is less than or equal to. Now change it to 28 over 53 plus 0.043. And all you have to do that, y'all, is second enter it back up and change the minus to a plus if you wanted to. Yeah, I think something's wrong. 28 over 53 plus 0.043. Make sure you typed it right, because it should be less than 1. Because these stand for probabilities, and your probability can't be more than 100% that something's going to happen. Right? So if it comes out more than 1, y'all know you did something wrong. What'd you get again? 571. All right. So these stand for the probability that someone chosen at random in high school watches football more than they watch basketball, and that with a confidence interval of 95, I'm 95% confident that that the probability that you watch more football than you do basketball is between 48.5 and 57.1% if you wanted to change the percents. Or you could leave it these numbers. It might, in a sentence, be harder to describe these numbers, but these are the actual probabilities. So the probability within a 95% confidence interval that you watch more football than basketball is 0.485 up to 0.571. That's not a real great probability, is it? All right, you want to try one totally on your own, and then we can check it? Go ahead. And we're going to stop. This is going to be our last one. I know there are 2 more problems on here, but we're going to stop with that because that's plenty, I think. We might do the other 2 tomorrow just if we feel like it's needed. Or we might leave those for you to practice before you take your quiz on Friday.